What's up, guys? Welcome back to Yoda Monk. And today we are going to discuss about another system design event, that is Google File System. Now, this is a very important paper and it will help you learn how the uploading and storage of files happens in default. We will also discuss about the future of Google File System. This is another landmark of the system design and software solutions ever achieved. Okay, so this one is one of the most important papers in distributed systems history. The original GFS paper came out in 2003. It shaped how we think about the distributed files, the fault tolerance, and consistency. But here's the thing, most system design courses treat GFS as an academic curiosity, something you read once and move on. But this is a mistake. GFS introduced ideas that every distributed storage system uses today, like HDFS, S3, Azure Data Lake, and GFS' own successor, Colossus. If you understand GFS deeply, you understand the design choices behind all of them. Also, I want to be direct with you. The GFS paper is a primary source document. I highly recommend reading it after this video. It is 15 pages, it is clearly written, and it will make everything in this video click. So let's go. Okay, so before we look at the design, let us understand what problem Google has been solving in 2003. Google was building a web crawler. They needed to store hundreds of terabytes, soon petabytes of crawled web pages. They needed to process this data with map-reduced jobs, large batch computation that read enormous files sequentially. The workload was unusual compared to the typical file systems. So the files were used not gigabyte, but hundreds of gigabytes or even terabytes per file. A typical Linux file system is optimized for millions of small files, but the GFS needed to be optimized for thousands of enormous files. So the reads are more sequential. MapReduce workers read a file from start to finish, and random seeks were rare. Writes were mostly append only. Web crawlers append new content to the log files. They do not go back and overwrite the data in the middle. The hardware environment mattered too. Google ran on commodity servers, cheap machine that fail frequently. In a cluster of 1000 machine, you expect several to fail every day. The file system had to tolerate hardware failures as normal operating condition, not an exceptional one. Now, this is fundamentally different assumption than what a traditional file system like ext4 or NTFS makes. Okay, so we'll go on to the functional requirement from the paper. It is to store and retrieve large files, support sequential reads and appends. It also supports concurrent appends from multiple clients. This is the atomic record append operation we will discuss in depth today. The non-functional requirements will be fault tolerance. It should survive the disk failures, machine crashes, network partitions without data loss. High throughput. This is for optimizing the bandwidth and not latency. Throughput for MapReduce jobs matters more than milliseconds response. Then we have the scalability, hundreds of terabytes initially and growing towards petabytes. Then we have the consistency. Here, this is the interesting part. The paper explicitly chose a relaxed consistency model, not strong consistency. We will discuss why later on. Let me do some quick estimation to ground the scale. The original GFS document at Google had roughly 1000 to 1800 machines per cluster. By 2010, Google was running GFS clusters with tens of thousands of machines. Now, file sizes range from 100 MB to several terabytes. The paper mentions a typical cluster size of 300 TB in 2003. This seems small today, but remember, this is 2003, and this file system that Google built from scratch was on commodity hardware. Now, the chunk size is 64 MB. Now, why 64 MB? We will explain that in the design section. But for the estimation purposes, a 1 TB file becomes roughly 16,000 chunks. If each chunk has a replication factor of 3, that is 48,000 chunk replicas, each chunk server might store 10,000 to 20,000 chunks. So you need at least 3 chunk servers for that single file. Though in practice, chunks from file are spread across many servers. Then we have the meta size data. The master stores metadata of all the chunks, the location, versions, and checksums. The paper states that GFS metadata for a large cluster fits in a memory on a single machine, roughly 64 bytes of metadata per chunk. For a cluster with 100 million chunks, this is 6.4 GB of metadata. It fits in RAM in 2003 hardware. Now, this is a key design insight. The master's metadata fits in memory, so all master operations are fast. If it stops fitting in the memory, the design would break. We will come back to this. It is what called original GFS at Google scale. GFS has three components: single master, many chunk servers, and many clients. Now, let me explain each of them. The master is a single process running on one machine. It is a brain of the file system. The master stores three kinds of metadata. The first is the file namespace, the directory tree, which file exists organized in a path hierarchy. The second is the mapping from files to chunk. Each file is divided into fixed chunk size. The master knows which chunks make up for which file in what order. Then the third is the location of each chunk. Which chunk servers hold a copy of each chunk. Now, all this metadata lives in memory. Operations are fast. The master processes thousands of operations per second. The metadata is also persisted to an operation log on disk. When the master makes a change, creating a file, adding a chunk, it writes to the log before acknowledging the trend. On recovery from the crash, the master replays the log to reconstruct its in-memory state. To keep log reply time short, the master periodically takes a checkpoint, a compact snapshot of its states. On restart, it loads the latest checkpoint and replays only the log entries after that checkpoint. Now we'll go into the chunk servers. Chunk servers are plain Linux machines running in the GFS chunk server processes. Each chunk server stores chunk as an ordinary file on its disk. A chunk is around 64 MB file. The chunk server serves read and write requests for its chunks directly to the clients. The chunk server does not know about the file namespace. It only knows about the chunk, identified by the 64-bit chunk handle, a unique ID assigned by the master when the chunk is ready. Each chunk is replicated across multiple chunk servers, typically 3. Now, this is the replication factor of 3. If one chunk server fails, the other 2 still have the data. The clients. So, the clients are applications, typically MapReduce workers or web crawlers. They link against the GFS client library. The client library talks to the master of metadata. Which chunks make up a file, where those chunks live. The client talks directly to chunk servers for the actual data reads and writes. Now, this is important. Data does not flow through the master. The master is only a metadata server. This keeps the master from becoming a throughput bottleneck. Okay, now let's go into the read part. Let me walk through a read operation step by step. The client wants to read bytes at specific offset in a file. Let's say the file is 200 MB and the client wants to read starting at byte 128 MB. Step 1 is the client calculates which chunk index this falls in. If chunk index is equal to floor of 128 MB divided by 64 MB, this is equal to index 2. Offset within the chunk is 128 MB mod 64 MB, which is equal to 0. Then step 2 is the client sends the master a request. Give me the chunk file and locations of the chunk index of this file. Step 3 is the master replies with a chunk handle and a list of chunk servers that the replicas. Step 4 is the client caches the metadata. It does not need to ask the master again for the future reads of the same chunk. Then step 5 is the client picks the nearest chunk server, usually the one on the same rack, and sends a read request. It's like give me n bytes from the chunk handle x at offset 0. Then step 6 is the chunk reads from the disk and returns the data. Now the master is contacted once per chunk, then bypassed. For the sequential reads, for a large file, the client reads chunk after the chunk directly from the chunk servers. The master sees very little read traffic. Okay, let's go to the write path and the mutation protocol. Writes are more complex. Let me walk you through a write carefully. First is the lease-based mutation protocol. For each chunk, one chunk server is designated the primary. The master grants the primary a lease, a time-limited permission to coordinate mutations to the chunk. The lease lasts around 60,000 seconds by default. While leases, the master needs to know who is the primary, but the master should not be involved in every write operation. That would make it a bottleneck. So leases let the primary manage the writes autonomously for the duration of the lease. The master only needs to be involved when the lease is granted or renewed. Then we will go to the write steps. Step 1 is the client asks the master who is the primary for this chunk. The master assigns a primary if none exists, grants a lease, and returns the primary and all replica locations. Then step 2 is the client pushes data to all replicas. Here is the clever part. Data is pushed along a chain, not in a star. The client sends the data to one chunk server. That chunk server forwards it to the next one in the chain. The last one acknowledges back along the chain. This pipeline model minimizes the time to transfer data to all replicas. Instead of the client needing bandwidth to send to all three replicas simultaneously, the chain spreads the load. Then step 3 is once all the replicas acknowledge receiving the data, the client sends a write request to the primary. The primary assigns a serial number to this mutation. The serial numbers define the mutation order. Step 4 is then the primary forwards a write request to all the secondaries. The secondaries apply the mutation in the same serial number order. Then step 5 is the secondaries reply to the primary when they have applied the mutation. Then step 6 is the primary replies to the client success or failure. Now, if any secondary fails to apply the mutation, the client retries the entire write. The write is retried until all replicas succeed or the client gives up. Then we talk about the atomic read append. GFS introduces a special mutation, the atomic record append. Normal file writes specify an offset. You say write the data at byte position X. The atomic read append says write this data at whatever offset GFS chooses and guarantee that this append is atomic. No two concurrent appends interleave their bytes. Now, why does this matter? In Google's infrastructure, many machines were writing to the same log files concurrently. If you use normal writes with explicit offset, you need an external log to coordinate. Now, this is complex and slow. With atomic record append, you just call append and GFS handles the coordination. Then you get back the offset where your data was appended. Multiple clients can append concurrently without coordinating with each other. The primary serializes the appends. It receives multiple append requests, assigns them offset one at a time, and instructs all the secondaries to write those in specific offsets. Now, there is one subtle thing. If an append partially fails, the primary succeeds, but one secondary fails. The GFS retries. This can result in data being written twice on the secondary that had a transient failure. That data appears twice at different offsets. Now, GFS accepts this. The paper says GFS guarantees that append happens at least once. Applications that need exactly one semantics must include unique identifiers in the records and deduplicate on read. This is the relaxed consistency model in action. Alright, let me talk about the consistency in depth because it is one of the most important and misunderstood aspects of GFS. Here we'll talk about consistency model. GFS defines file region stakes as one of three types. First is define. Define. All clients see the same data and the data reflects the mutation. This is strong consistency. Consistent but undefined. All clients see the same data, but the data may be a mix of multiple concurrent mutations. The content is the same everywhere, but you cannot predict what you will see. Then, inconsistent. Different clients may see different data. We avoid this. Now, when does each state occur? A successful serial write, no concurrent writers, leaves the region defined, clean, and consistent. The concurrent successful writes leave the region consistent but undefined. The data written by each client is a valid mutation, but each client's data occupies which byte range is non-deterministic. A failed mutation leaves the region inconsistent. The atomic read appends are always defined but may have gaps or duplicates. The paper is explicit about this. GFS is not POSIX compliant. Traditional Unix semantics say if you write to offset X, you can immediately read back what you wrote. GFS does not guarantee that in concurrent scenarios. Now, why this? Because relaxed consistency is simpler to implement at scale. Strong consistency requires all replicas to agree before acknowledging a write. That is expensive at scale. Relaxed consistency allows the system to be faster and more available. Now, Google's applications were designed around this model. MapReduce jobs writes the output file atomically. It writes to a temp file, rename when done. Web crawl logs use atomic read append and include deduplication logic. Now, we'll go to the next section, that is fault tolerance. Fault tolerance is where GFS really shines. Let me walk you through the failure scenarios. First, we have the chunk server failure. This is the common case. A chunk server crashes. The master detects this through the missed heartbeats. Each chunk server sends a heartbeat to the master every few seconds. After a timeout, say 10 minutes, the master marks the chunk server as unavailable. The master scans all chunks that had replicas on the failed chunk server. For each chunk that now has a fewer than 3 replicas, the master schedules re-replication. It finds a chunk server that has the chunk and instructs it to clone the chunk to another chunk server. Now, re-replication is throttled. You do not want to do re-replication to saturate the network. The master manages a re-replication priority queue. Chunks with only one remaining replica get top priority. Another failure scenario is the disk corruption. A disk can silently return corrupted data, a bit flip, a bad sector. Then GFS defends against this with checksums. Each chunk is divided into 64 KB blocks. Each block has a 32-bit checksum stored separately. When a chunk server reads a block, it verifies the checksum. If the checksum fails, the chunk server returns an error to the client and reports the corruption to the master. The master schedules the chunk to be re-replicated from a healthy replica. Checksumming is done on read, not on write. This is efficient. You only need to do the extra work when the data is actually accessed. Then we have a master failure. Here is a spoof. The master is a single machine. If it fails, the entire file system becomes unavailable. Now, GFS's answer is the operation log and shadow master. The operation log is replicated to several remote machines in real time. When the master writes its log, it must get acknowledged from at least one shadow before it confirms the operation. Now, this ensures the log is durable even if the master machine fails. Now, the shadow masters maintain an almost current copy of the master state by replaying the operation log. They serve read-only operations, file metadata reads when memory master is unavailable. This provides read availability during the master failures. On primary master failures, an operator manually promotes a shadow master to the primary. Now, this is not automatic. The paper describes this as a human in the loop process. Now, this is a deliberate choice. Atomic failure is complex. You need a consensus algorithm to decide who becomes a primary. Either use Paxos or RAF. In 2003, the Google team decided the simplicity of manual failure are worth the downtime cost. Now, how long does a recovery take? The master replays the checkpoint and the operation log. With the periodic checkpointing, this takes a minute or a few minutes. During this time, the file system is unavailable for the writes. Okay, now we'll go to the next section. That is, why do we need 64 MB chunk? We talked about this earlier. I told you that I will tell you about this later on. So let me explain the chunk size choice because the interviewers asked this. Now, 64 MB is a large by file system standards. NTFS has 4 KB cluster. EXT has 4 KB blocks. Then why did GFS choose 64 MB? There are 3 reasons. The first one is the reduced master metadata. More bytes per chunk means fewer chunks per file. Fewer chunks means less metadata in the master. And a 10 TB file with 64 MB chunk has about 160,000 chunks. With 4 KB blocks, the same file would have around 2.6 billion blocks. The master cannot hold 2.6 billion metadata records in the memory. It can hold 160,000. The second is reduced client-master interaction. The client caches the chunk location. If the chunk are large, the client can read through a large chunk without calling the master again. For sequential reads, which are 99% of the GFS workload, the client talks to the master once per 64 MB, not once per 4 KB. The third is the better network throughput. Setting up a TCP connection to a chunk server has its overhead. Transferring 64 MB amortizes that connection setup cost over more data. Now, the downside of large chunk is small files. A file smaller than 64 MB occupies exactly one chunk. Many client accesses that one file means many clients hitting the same chunk server for the same chunk. Now, this is a hotspot problem. GFS mitigates this by allowing the client to read from multiple replicas and by setting up higher replication factors for hot small files. Now, let's do a deep dive. First, we'll talk about the master operations. The master is responsible for all namespace operations: file creation, deletion, renaming. These are the atomic operations protected by the logs on the namespace tree. Then we have the chunk creation. When a file needs a new chunk, the master picks these 3 chunk servers to host it. The selection considers disk space. You don't want to overload one server with too many new chunks. And rack placement. The 3 replicas should be on different racks for rack level fault tolerance. Now then we have the garbage collection. When a file is deleted, GFS does not immediately delete the chunk data. The master logs the deletion and renames a file to a hidden name. The actual chunk data is deleted lazily. The master scans the chunk location periodically, finds the chunk that belongs to no file, and instructs the chunk servers to delete them. Then we have the lazy deletion in simpler and safer way. If a delete is accidentally logged but the data has not yet been fully replicated, the immediate deletion would be lose the data. Lazy deletion gives the same time to recover it. Then we have the chunk server operation. Chunk servers periodically send the master a full list of their own chunks. This is called their chunk report. The master uses this to verify its understanding of the chunk locations. On startup, the master does not know which chunk server has which chunk. So it learns this from the initial chunk reports. This design choices means the master does not persistently store chunk location on the disk. The chunk locations are built from the chunk server reports on every restart. This avoids a whole class of synchronization bugs between the master's disk state and chunk server's actual state. Okay, how do you monitor GFS in production? The first is the master metrics. The operation throughput, metadata reads and writes per second, the operation latency like P50, P95, P99 for the namespace operations, the chunk creation rate, number of chunks below the application threshold, this is critical. If this number is growing, chunk servers are dying faster than read application can keep up. Then we have the memory usage, that is metadata memory consumption. If this approaches the machine's RAM limit, you need to intervene. Then we have the chunk server metrics. In chunk server metrics, we have the disk utilization per chunk server and the overall cluster. Read and write throughputs per chunk server. Chunk sum failure rate, how often are corrupted blocks being detected, then the heartbeat latency to master. Then end-to-end metrics, the write success rate. What percentage of client writes succeed on the first attempt? The read success rate, read replication rate, how fast is the system restoring chunks to the target replication factor. Then we have the alerting. Now we alert if any of the chunk with replication factor below 2 is for more than 5 minutes. This is a potential data loss risk. Then we alert on master heartbeat loss, any disruption to the master availability. We can also alert on chunk server disk usage above 85% across more than 20% of the cluster. Now, approaching capacity also is an alert issue. If we have a growing write failure rate, then also something is wrong with the mutation pipeline. Now, this section is very important because we did move evolute from GFS to Colossus. Now, let me talk about what happened to GFS after 2003. Now, GFS served Google well for a decade, but several limitations became acute as the company grew. The single master became a bottleneck, not a performance bottleneck. The master was fast, a scalability bottleneck on metadata capacity. The same file problem became severe. Gmail, Google Photos, and other consumer services created billions of small files, and GFS was not designed for this. The manual master failover was an operational pain point. Recovery time measured in minutes is acceptable for the batch jobs, unacceptable for the production services serving the user traffic. So, Google developed GFS2 around 2010, later formalized it as Colossus. The Colossus distributes the master across multiple machines. Metadata is stored in a big table, Google's distributed table store. This removes the in-memory scalability constraint. Colossus can handle around 100x more files than the original GFS. Colossus also introduced Deep, a distributed storage layer that replaced direct local disk. Storage and computation are disaggregated. Chunk server nodes are replaced by the D nodes, stateless compute nodes that read from and write to a shared storage layer. This makes the scaling easier. Colossus supports erasure coding for cold data. Files that have not been accessed recently are re-encoded using the read Solomon. The storage cost drops around 40%, and on first access, the data is decoded in real time. Colossus also introduced per client QoS. The different Google services have different latency requirements, so Colossus can prioritize latency sensitive reads from production services over bandwidth intensive reads from batch jobs. Now let's do some of the tool comparison. Let me compare GFS with its contemporary and the successors. Let's do GFS versus HDFS. HDFS is Hadoop distributed file system and is the open source re-implementation of GFS. Facebook, Cloudera, and Yahoo open sourced it starting from 2006. The similarities are master chunk server architecture called name node and data node in HDFS, same chunk-based storage model, the same replication factor of 3 by default, same optimization for large sequential reads and appends. Now here are the differences. HDFS uses 128 MB blocks by default versus GFS 64 MB. Now, larger blocks further reduce the name node metadata size. Name node high availability. Original HDFS has the same single name node spoof as GFS. HDFS added HA name node support in version 2.0. The two name nodes in active standby mode using Zookeeper for the failover. This is automatic failover, unlike GFS's manual process. Then the consistency. HDFS provides HDFS FS data output stream, one writer, semantics. Only one client can write to a file at a point. No concurrent append like GFS's atomic read append. This is actually stronger consistency than GFS, but less flexibility. GFS's concurrent append was used extensively by Google. Then the ecosystem. HDFS won the open source data processing ecosystem like Hive, Spark, Edgebase, all run on HDFS. GFS was never open source. Now, when you should use HDFS? If on-premise data centers are there or if you need deep integration with Hadoop's ecosystem. Spark on HDFS is still common in enterprise data platform. Now, if we compare GFS, HDFS to S3, S3 is fundamentally different. It is an object store, not a file system. GFS and HDFS expose a file system API. You can create the directories, list files, rename files, append to files. S3 is a flat key value storage. Key looks like file path, but there is no actual real directories. Now, why does this matter? Now, rename is metadata operation in HDFS. Now, in S3, renaming directory means copying all the objects under that prefix and deleting the originals. Now, this is slow and non-atomic. Now, appending to a file in HDFS is native. In S3, you cannot append, you write the whole objects. Appending means reading the existing object, appending locally, and writing the entire object back. Or use S3 multipart upload to assemble a newer version. So, why do you use S3? This is for zero operational overhead. No name node to manage, no rack topology to configure. Amazon manages all of that. Now, if you are doing a massive scale, S3 stores trillions of objects. It serves the scale no single Hadoop cluster can manage. Now, for integration purposes, every cloud service integrates with S3. EMR, Athena, Glue, Lambda. The S3 API is the de facto standard for cloud object storage. Today, most new data systems use S3 compatible storage rather than the HDFS. Even Spark and Pesto now run natively on S3. The compute storage separation that Colossus pioneered is the industry standard. Now, what about GFS versus Azure Blob Storage? Azure Blob Storage is Microsoft's equivalent of S3 and object storage. Same trade-offs between S3 and GFS. The distinction worth mentioning is Azure Data Lake Storage Gen 2 layers a hierarchical file system namespace on top of Azure Blob. Now, this gives you directory rename and atomic operation while keeping the blob storage backend. It is a hybrid, closer to HDFS semantics with cloud scale economics. Now, when to use each one? Let me give you a clear decision criteria. HDFS should be used when you want to use on-premise on the private cloud data, Hadoop ecosystem, the Hive, Edgebase. You need native append and concurrent writers. You should use S3 or the Azure Blob Storage when you need public cloud, you want zero operational overhead, you need massive scale, your workloads are primarily read-heavy or write ones. You use GFS or Colossus when you work at Google. It is the propriety. You are not building this. Now, a follow-up question might be, if you are building a new data platform today from scratch on AWS, where does HDFS fit in? Honestly, it probably does not. S3 storage, EMR or Glue or Athena are compute, fully managed, no name node to operate this. So HDFS is legacy at this point for most of the new system. All right, so let's recap. Now, GFS is a single master, many chunk server distributed file system designed for large-scale sequential reads and appends on commodity hardware. The single master is programmatically accepted in 2003, solved in Colossus by distributing the master. Now, the 64 MB chunk reduces the master metadata and client master interaction. The mutation protocol uses leases, pipeline data push, and a primary secondary model. The atomic record append enables concurrent writers without external log at the cost of at least one semantics. The relaxed consistency is a deliberate choice. Application must be written to tolerate duplicates and the partial data. Fault tolerance comes from the replication factor 3, check summing, and the operation log. The metadata in memory constraint was the fundamental scalability limit that drove the evolution of Colossus. When comparing GFS to HDFS to S3, GFS and HDFS are file system optimized for big data batch workloads. S3 is an object storage optimized for cloud scale with zero operational overhead. New systems should default to S3 compatible object storage. Now, this is Google File System for first principles to the production evolution. If this was useful, subscribe to Yoda Monk. I will put on more deep design content every week. See you in the next one.